Hmm? What? Oh, this slide? Okay. This global. Okay, so the topic for today is global optimization. Okay, actually, for global optimization, it's recently it's quite it's developed very fast, and we have a very good tools. Yeah. Well, in the old day, of course, global optimization deal with. Yeah, what is global optimization first? I will show you what is global optimization. And let me, yeah, I can show you this one. Sorry, I have to unshare it first, and then because I have to copy some command from my slide. Yes, and what I want to show you is the unique feature of the global optimization, and why do we need it? Now consider this figure. This is one of example we call global optimization. Why is important? And it's almost felt by other solution technique we learned so far. You see it contains so many local optimization, right? Local optimum point, right? We have too many minimum points. Local minimums, and also local maximum point. For example, you see, previously we deal with what technique we learned? Line search, right? What is the idea of the line search? We choose one direction and then find the lambda, right? Step size, and then you choose another direction, and then anyway, you start from trial points, initial points, trial points, and then your iteration lead you to one minimum point or maximum point, whatever it is. Then it will stop there, right? And you see that if you want to escape from one minimum point, you have to select different initial point and then try again, right? So more or less random process. Okay. So for this kind of surface, it's, well, it's quite difficult. It's challenge for traditional algorithm. Okay, so this is the reason why we have to deal with global optimization like this. Yeah. And even you don't use light search, you use simplex Niedermed. Again, you start from 3 points, right? And then, wow, it's move toward some local minimum again. You cannot escape the local minimum point because it's attract the iteration, well, converge to local minimum point or maximum point. Okay, so how can we deal with this kind of things? I mean, global optimization. This is, now we consider the objective function alone without constraint, right? If global optimization having constraints, wow, it's become more and more difficult, okay? But for this one, the idea is, well, random it, just random it, wow, and then you repeat the solution, maybe you, well, divide the search region to multiple space, and then you search each space, and then you try it. Or you can use some heuristic method like genetic algorithm, simulated annealing, pattern search, particle swarm, or differential evolution. But those things depend on random number. Okay. In, well, in any step of the algorithm, it involves random. Okay. And then for example, for genetic algorithm, I will explain you more about it. But it's mimic the nature process because, well, for example, in nature, because you know the life view, what's it, depends on evolution, right? Depends on the environment you live. If you cannot survive there, of course you're going to extinct. Right? So you give good gene to your son and your grandson, and so on, something like that. If you can compete with others, if you cannot compete with others, of course you can extinct somewhere. Okay, so it follows that it mimics the natural selection process. Okay, so, well, stop share this one first, and then what is it, keynote? Okay. Okay, so we don't have time to write the code by ourselves. Okay, we're going to use global optimization toolbox, which is well, provided by MATLAB. Of course, you need MATLAB. Okay, I don't know which version of MATLAB you are using, but, well, I use the latest version. And for global optimization toolbox, it's very convenient currently. Yeah. You can use global optimization toolbox to solver to optimize non-smooth function. Okay. Remember that last time when you deal with the penalty function, well, you encounter some difficulties, I think, when at the border when you introduce the penalty function, right? Because you introduce discontinuity or non-smooth function at that point, right? But for non-smooth function, for global optimization toolbox, it can deal with that, no problem at all. And actually, there are two approaches in global optimization toolbox in MATLAB. Oh, it should be toolbox. Okay, toolbox. The first one is problem-based approach, and the second one is solver-based approach. What is the difference from problem-based approach, solver-based approach? For problem-based approach, you don't pay attention to the solver. Okay, let the toolbox do it by itself. Like in YAOMIP, you remember YAOMIP, right? Once you code you write the model, you don't have to pay attention to the solver much. As long as the solver are available, it will select the best one for you. That is problem-based approach. But for solver-based approach in global optimization toolbox, that means you pay attention to the solver, and then you select the solver, you tune the solver by yourself, which is troublesome. It is. Okay, so I recommend to use the problem-based approach for a simpler way to set up and solve the problems. Okay, because we want solution. Of course, during the process to find the solution, it's enjoyment. But we want solution, not the process. Okay, so for problem-based approach, it's easier to set up and debug, and easier to run different solver on the same problem. That means you code your problem once, and then let the rest the toolbox do it. Select the best solver for you and obtain an appropriate solver automatically. Okay, also automatically speed the solution of problems where the objective and nonlinear constraints are calculated in the same time consuming function. Okay, so I mentioned to you that previously, actually the global optimization, I mean not toolbox, I mean the global optimization problem. Wow, we deal with it a long time ago. It's not a new topic. Even genetic algorithm, it's invented maybe 50 years ago. Okay, wow, 40 years ago, I don't know. Yeah, but you know, you can expect the more powerful of such an algorithm because those algorithms depends largely on computational power. If you have more computational power, then of course the algorithm will be more powerful. Okay, so this is a workflow for problem-based optimization, problem-based approach in MATLAB. First, you have to create an optimization problem object by using optim problem. This is the command in MATLAB. Okay, use the command optim problem, and it's accept more than one parameter, but the important parameter is the objective sense, whether you want to maximize or minimize it. Okay, if you want to minimize your objective function, you use minimize, not maximize. Okay, and probe is the name of the object you created. Okay, and if we know that this is the optimization problem. Okay, oh, one thing, you need global optimization toolbox. Okay, when you install MATLAB, you have to select the globe optimization toolbox. And then once you create an optimization problem object, then you create name variables by using optimvar, this command optimvar. It receives the value, lower bound, upper bound, right? Optimvar. I will show you in the command also. Help optimvar. Okay. Okay. Create optimization variables. Okay. Syntax, it's you create X optimvar and then name. Okay. Okay. Once you define your variable, then you define the objective function. Okay. In the problem object as an expression in the name of variables. Okay. Define the objective function in the problem object. Remember that you create optim problem, right? Optimization problem. The name is prop. Then prop dot objective. It's the objective function, the function you want to optimize. Then you define the constraint for the optimization problem. Okay. For example, this one sum was sum. Okay. You join on the define on the constraint, connect all the constraint defined to the optimization problem. Okay, here. And you can skip here. This is just for nonlinear problem. Okay, set an initial point as structure. Yes, and the important thing, once you define, you create optimization problem, you define the objective function, you define the variable, you define the constraint, then solve the problem. Solve the problem by using solve. This one, solve, and take one input. It's problem you define. Okay, so prop. Okay, in case of nonlinear function, you can input the initial point, right? And this can be initial point as a second input, second parameter. Okay, I will show you the example. Okay. An example. Yeah. For this one, load particle, it's an example in the MATLAB where, the data is already there. Okay, so we just load that data. But for other problems, you have to define your problem by yourself. This problem, it's curve fitting. Okay. And this data, load particle, yes, particle data contain C and, it cannot display here. C and D, right? We have C, right? Yeah. And D data. Size of C. Yeah. data C, it's 2000 by 400, and size of the size of, oh no, size, okay, 2001, okay, and X is Optima X, no, MATLAB. Sorry, Optima, okay. And define the lower bound of X. Next is define the prop, okay, optimization problem, which is prop optim problem, okay. This is our objective function. We define it first, okay, and this, now we connect the, attach the objective function to our optimization problem. Okay. We don't have constraint, this one. We have only boundary. And the last one, we solve the problem. Okay. We can solve this problem already. So where is X? Okay. It show X. No. Show X. Sorry. Yes. Okay. So this is a least square problem which passes data. We pass data and then we solve the optimization problem using the global optimization toolbox in MATLAB. Okay, so well, next one. In MATLAB, of course, in global optimization toolbox, there are so many algorithms available. I will show you some of the algorithms and compare the algorithm we have. For we are dealing with this objective function, okay? For this one, this objective function where the objective function is 20 plus x squared plus y squared, and then subtract by 10 of cos 2 pi x, right? Plus cos 2 pi y. Okay, we have two variables, X and Y. And the, what it's, I already show you, right? The surface of that, this function is look like this. Yes, this one. This function. So we're going to apply difference algorithm to solve this problem. Okay. We start from scratch. Okay, clear all and then CLC. And first we define the function. Let me share the MATLAB first. Okay. Okay. And this function, okay, no need to plot. First, well, the starting from define the optimum, right? Okay. And now define the optimization problem. Okay. And define the objective at the same time. The objective is this one. I define the initial point. Some algorithm need initial point, but some algorithm doesn't need anything. Okay. The first algorithm, it's F-min-C, okay? This algorithm actually use quasi-Newton method, which is not global optimization, okay? But what we can expect from F-min, you see, F-min, you see, it's unconstrained F-min, okay? F-min with unconstrained. Well, just for comparison, okay? It's not global optimization toolbox, but, you know, it will struck somewhere because it has no algorithm to escape from local minimum point. Okay. So the this is the result. This is X, Y, and objective function, which is a result from this F-min-C algorithm. Yes, minimum point, of course. Yes. So F-min-C quickly reach the local solution within its starting basin because it has so many loop, right? Minimum point. but it will, well, approach to the next, adjacent local minimum, okay, and quickly converge to local minimum point, but does not explore outside the basin, that basin at all, because it has no algorithm to escape that basin, okay. And F-min unconstrained, F-min unc use automatic differentiation and takes very few function evaluation to reach an accurate local minimum point, okay. So now we will implement the global optimization toolbox, okay. The first one is pattern search. For pattern search, yes, I supply them, I input the initial, okay, and this is the algorithm, this is the command to solve. Nope. Again, come on, it's so p solve x0 solver pattern search, okay. So it's converged successfully, but don't expect much because global optimization, it's always converge. You got a solution, but you cannot guarantee that solution is satisfying the minimum point or not, okay. The value we got, you see that it's smaller than what we obtained from F-min and C, right? Previously, we got 12 something. Yes. Pattern search try to explore the whole area and obtain this value, 4.9748. So, but pattern search takes more function evaluation, okay? It's evaluate objective function more, it use computational load higher than what we need for F-min and C, okay? But it searched through several basins, arriving at a better solution than F-min and C, okay? This is pattern search. This should be this. I don't know what is this. Yes. Okay. Now we move to the next algorithm, GA, genetic algorithm solver. For this one, as I told you that genetic algorithm use random, okay, use random number in the process in its algorithm, okay. So we have to define the ing plus random number generator for reproducibility, okay. You have to, well, you must understand the random generator in computer first. Random generator takes one parameter, okay. If you want to repeat your result. I mean, in case you use random number, and if you want to repeat it, you have to supply the same parameter for a random number. Okay. If you don't define anything, the random generator will take the clock of the current time as a key parameter, as a parameter for the random generator. Okay. So yeah, we use ing default. Okay, we use clock. I mean, yes. And then we random the initial. Okay. And then we solve it. Oop. Again, I hate this. Must be the same. Okay. Okay. Luckily, we got the solution, which is very small. Objective function, you see, close to zero, even better than pattern search. Okay. But we cannot guarantee that every time we run, we will obtain the same solution because we are working with random number generator. If you want to reproduce your result, you have to define the parameter for the key for your random generator. Okay, let me repeat it again. You see, this time we obtain different value. Okay, but of course it's better than pattern search, but it's not the same value we obtained previously. Okay, because we don't supply any parameter to the random generator. Okay. Okay. Yeah, please, well, break for 5 minutes. I got a call from Oh, sorry. I mute my microphone. It's okay. It's okay. Yeah. Now we using simulated annealing. Yeah. No one remind me that I mute my microphone. Yes, this is result from simulated annealing. You change it every time you got obtain different solution. Yes, different value. Okay. Mm. And the last one, I think this is the last group of last algorithm in the global optimization problem. It's surrogate optimization. Okay. Again, this one use random number. Yes, and and you need the bound of the your variables. Yeah, bound of x and y. Mhm. Yes. You run it again, you obtain different things because it's used random number. Okay. Any questions regarding this? I think
Will
it's
this be
quite
in the exam?
yes. Say again.
Oh, will this be in the exam?
Oh, we are not talking about exam yet. We have not finished today class. Okay.
Oh,
You discuss
okay.
it? Yeah, later. Any questions? Hmm? You can try it by yourself. Okay. Maybe you try it on the previous assignment, the optimization problem you in your assignment. Mhm. Okay, so I will explain you about some global optimization algorithm here. I choose one. The most famous one for me, it's genetic algorithm. Well, it's genetic algorithm developed as early as 1962, right, by John Holland's work on adaptive system. Okay, and well, later he published a book on adaptation in natural and artificial systems. Okay, and later developed it. But in 1992, well, the John Kosa used the genetic algorithm to evolve program to perform certain tasks, and it's called genetic programming. But the idea is on genetic algorithm, of course. So what is genetic algorithm? Genetic algorithm we call GA. It's a search technique used in computing to find true or approximate solution to optimization and search problems. And GAs are categorized as global search heuristic. Okay. So GA doesn't use for all GA algorithm, but when you say GA, actually it composed of different algorithm, of course, but the same class. Yeah, but those algorithms are categorized as global search heuristics. And well, particular class of evolutionary algorithm. And the technique inspired from evolutionary biology. Okay. So you start from population, and then those first population evolve to the several generation through the what is it, crossover and mutation, something like that. So wow, and you evaluate the fitness through the maybe objective function and other thing. For example, you have a population of 100 points at the beginning, and you evaluate those 100 points with your objective function. Of course, those individual with what's it with better objective function obtain higher rate for reproduction in the next generation, something like that. Okay, then it evolved through generation, and then well, it stopped somewhere. Okay, so in each generation, the fitness of individual in the population is evaluated, and when we say fitness, we mean the objective function plus constraint. If those individual meet the feasible or not, meet the constraint or not. And you create new population, and then new population, of course, evaluate again with fitness, with objective function, and then algorithm, well, repeat themselves itself for generation, and then the algorithm stop when maximum number of generation has been produced or satisfactory fitness level has been reached for the population, something like that. Okay, so we have, from the vocabulary viewpoint, we have individual. Individual means, in GA, individual means any possible solution. Okay, and population means group of all individuals. So you see that in line search, some algorithm, we use only one point at each iteration, right? or some algorithm like simplex use at each iteration you have 3 points, right? But for genetic algorithm, it use population. I mean, maybe 100,000 points for each iteration. Okay, you cannot work with only 1 point at a time at each iteration. You need a group of points. We call it population. Okay, and the next one is fitness. What is fitness? Fitness is target function that we are optimizing. Okay, it can be objective function. Okay, but in GA we always call fitness. Okay, and the fitness also cover the concept of feasible points, also feasible region. Okay, what else? We have traits. Trait is possible aspect of an individual. Okay, and genome. Genome is a collection of all chromosomes for an individual. Okay. So for genetic algorithm, we start with a large population, and now normally we randomly generate it. Okay. And so many works report or invent techniques to generate just the initial population. Okay. And the algorithm repeatedly do the following. First, evaluate each of the attempt solutions. Okay. And keep a subset of the best solution and then reproduce. Use the solution to generate new population or reproduce new points. Okay. And then repeat this. Okay. Once you generate new point through crossover and mutation, you have to evaluate it again. Okay. And then keep a subset of the best solution and then repeat it. And then you quit when you have satisfactory solution or you run out of time. It depends. Okay. The concept is quite, of course, if you run forever, finally you will reach, maybe you reach the minimum point. But it consumes a lot of a computational load. And you cannot rely on genetic algorithm because, it has no guarantee at all whether the solution you obtain, can be, is a real minimum point. Okay. But you can guarantee that, at least you got something. But maybe it's not, it's not a local minimum point. Okay. Any questions? For other techniques like particle swarm, the algorithm is different from genetic algorithm, but the concept it's more or less, because it's used random and reproduction and evaluate the solution, something like that. Okay, but anyway, at least you learn how to solve the global optimization problem, okay, using available tools. Okay, so any questions? No? Any question from Zoom? No? Okay. So yes.
Start that calculations. Choose the starting point with given or just random.
Repeat again. What is your question?
Start with the bad population. Start with that population. It says.
We start with a large population of randomly generated. Yes. So your question is?
So it should be just random numbers. Numbers that no satisfy the function.
Yes. We start it randomly. But for some algorithm, it's not totally random. I mean, well, it's, for example, in some algorithm, they divided the area first from to a small area and then random in that small area, something like that. Yes, it's possible. Okay. Oh, well, what do you think about exam, final exam? When should we have exam? When? We have thermodynamics on advanced thermodynamics on 6, maybe 12. 13 is okay. What do you think? Yes. I have 1 week to finish it for grading. Yes. Yes, it should be 13. What do you think? 13 is okay? Okay. Yes. So,
Sorry,
Good.
Professor.
Yes.
13th of November?
December. We cannot. No,
Yeah,
it's already passed. Huh?
13th of December. Okay.
Yes. Exam on 13 November. No, December. Sorry. And at what time? Morning or afternoon? Afternoon. Yes. Okay. Yes, that is okay.
So is this the last class?
Yes, the last.
So what would be the topics in the exam?
Yeah, it will cover all the nonlinear programming, line search, what you use in your assignment, also global optimization.
For global, we may need like more example.
What do you mean?
I don't think there's enough examples in the like for global optimization. So could you provide more? Maybe.
Well, you just well, what was it? I will ask you about the general characteristic of it. I know that you cannot calculate it in because you need computer, right? You have it's run in a repeated manner. You cannot, of course you can do it, but it's meaningless if you calculate it 1 or 2 iteration, something like that. So normally for global optimization, well, you don't have to calculate by yourself, of course.
I see.
Yes, but at least you must know what is it, important characteristic of this kind of algorithm compare with the the other techniques like gradient based algorithm or line search. Yes.
Sir, how would the format of the test be?
Format.
Hmm.
Yeah, of course, on site.
Do we need computer?
No, you don't need computer. Okay. You need just calculator.
Okay.
Yes, of course, you can expect for some calculation like what's it, line search for 1 or 2 iteration. Okay, simplex method for 1 or 2 iterations, something like that. Oh yes, of course. Yes, constraint. Excel. No, Excel. Exterior, right? Exterior, interior function. Yes. Yes, you need some calculation also. Pardon?
Use calculator or Excel?
Calculator.
Calculator only.
Yes. Yes. Okay, so we finished today.